Hey my friends, I hope you're having an amazing day. For today's science video, we are going to do another read-along of an amazing book I found at our school library called Light Waves. But before we do that, I wanted to do a review of our sight words this week. Can anyone remember one of our sight words this week? The first one is it. That's I-T, it. What about another sight word this week? The second one is is. That's I-S, is. And what was the third one we learned? In. I-N, in. Great job at that review, my friends. And now it's time to read our book. Light Waves by David A. Adler, illustrated by Anna Raff. We need light to see. Plants need light to grow. Animals need plants to eat. Since plants and animals are the food we eat, we would have no food without light. Without light, we just could not survive. We need light, but what is it? You can see it, but you can't touch it. You can't hold it, carry it, taste it, or smell it. Light is a form of energy. Energy is the ability to do work. Energy comes from the sun in the form of sunlight. It is transferred to the grass, then to the cattle. From the cattle, it is transferred to the hot dogs. From the hot dogs, it is transferred to us. You can't make energy. You can't destroy it. Energy can only be transferred, moved, from one thing to another. For example, sunlight is a form of energy. It helps grass grow. Cows eat grass, and the grass they eat helps them grow. Later, meat from these cows is used to make hot dogs. Even later, people get energy from eating those hot dogs. Much of our light comes from the sun. Light from the sun, solar energy, can be collected. It can be used to power our machines and heat our homes. The sun is almost 93 million miles, or about 150 million kilometers from Earth. That's a long way. It would take a car speeding at 60 miles, or about 97 kilometers an hour, more than 170 years to travel that far. But it takes sunlight just 8 minutes to travel from the sun to Earth. Light travels at the tremendous speed of 186,282 miles per second, or 299,792 kilometers per second. That's fast. Nothing travels faster. When we see light, we're seeing streams of light waves. These streams are made of photons. Photons are tiny bits of light that travel together in wavy streams of light. You can think of the waves as very long bands with crests, high points, and valleys, low points. Waves of light with their crests and valleys travel in straight lines. Let's show that light waves travel in straight lines. This is what you will need: a flashlight, a book, 2 cardboard tubes cut from rolls of toilet paper or paper towels, some tape. Stand the book up on a desk or table with the front facing you. Hold the flashlight close to the book and turn it on. The front of the book is bathed in light. The back is not. That's because light waves travel in straight lines. They travel straight at the book. They do not go around it. Next, tape the 2 cardboard tubes together. You now have one long tube. Take the tubes and flashlight to someplace dark. Shine the flashlight through one end of the tube. The light should shine through the end and out the other end. Now, where the 2 tubes are taped, bend them so they no longer form one straight tube. Shine the flashlight through one end of the tube. The light waves will not shine through the other end because light waves only travel in straight lines. Light waves travel through air in straight lines, but you can bend it. Let's bend light waves. What you will need: a clear glass and a drinking straw. Fill the glass at least halfway with water. Put the straw in the water. The straw seems to bend at the water line. The straw looks bent, but it's not. Take the straw out of the water. It's straight. The straw seemed to bend when it was in the water because light waves travel more slowly through the water than through air. When light waves travel at different speeds, they seem to bend things. This is called refraction. Light won't travel at all through this book. It doesn't travel through stone or wood. It won't travel through you. Stone, wood, books, and people are opaque. Light won't pass through them. Opaque objects and light rays form shadows. Let's create shadows. What you will need: toy blocks, flashlight, a room that can be darkened. On the floor or on a table, pile the blocks into a tower. Darken the room, turn on the flashlight, and point its light at the blocks. One side of the tower is bathed in light. You can see the blocks clearly. Look directly behind the blocks. There's a dark shape on the floor or table. It's roughly the same shape as the tower of blocks. That darkened shape is a shadow. Shadows are formed when opaque objects block light rays. Light does travel through some things. Of course, light travels through air. Light also travels through glass and clear plastic wrap. That's because air, glass, and clear plastic wrap are transparent. Light doesn't travel completely through wax paper, frosted glass, or honey. If you look through a sheet of wax paper, whatever is on the other side of the paper seems blurry. That's because wax paper, frosted glass, and honey are translucent. Light waves bounce off surfaces such as apples, the hoods of cars, and large bodies of water. When light waves hit a shiny and completely flat surface, the light waves bounce straight back. Then you get a reflection of what is facing that shiny flat surface. A mirror is shiny and flat. It reflects just about all the light that hits it. The light bounces directly off the mirror, so you get an almost perfect reflection of whatever is facing it. Imagine you're in a playground and you throw a ball against a wall. The ball bounces right back. That's what happens when you look at a mirror. The light waves bounce right back. When you look at a surface that's not as shiny and flat as a mirror, the light rays don't bounce right back. They become somewhat scattered, so you don't get an exact reflection. Get a large, shiny, metal soup spoon. It's shiny like a mirror, but it's not flat. Look at the back of the spoon. You can see yourself, but it's not an exact reflection. Your reflection should be somewhat elongated. To understand why your reflection is elongated, imagine you are in a playground with a huge half globe. If you throw the ball against the top part of the globe, the ball bounces up. If you throw the ball straight ahead, it bounces straight back. If you throw the ball against the bottom part of the globe, the ball bounces down. That's what happens when you look at the back of the spoon. The light waves do not all bounce straight back. Light waves bounce up off the top of the spoon and down off the bottom. Look at the inside, shiny bowl of the spoon, the side that scoops up soup. Your reflection is upside down. To understand why your reflection is upside down, imagine you walk behind the huge half globe in the playground and there's no back to it. It's a large concave shape. If you throw the ball down against the bottom part of the globe, the ball bounces up. When you look at the front of the spoon, the light waves that strike the bottom of the spoon bounce up, and light waves that strike the top of the spoon bounce down. Up goes down, and down goes up. The reflection on a shiny, concave shape is upside down. Pure light looks clear, as if it has no color. We call that white light. But white light is not really colorless. It's made of a spectrum of colors, a prism. A triangular column of glass can be used to split white light into its 7 colors: red, orange, yellow, green, blue, indigo, and violet light waves. Think again of light waves as wavy bands made up of tiny bits of light. These bands of light have crests, high points, and valleys, low points. What makes the color of light waves different is the distance each color has between its crests. With the red waves, the distance between the crests is greatest. The distance is smallest with the violet waves. We see objects because light waves are reflected off them, but not all light waves are reflected. Some light waves are absorbed. When an apple appears red, it's because red light waves are reflected off the apple. The other color waves are absorbed. When a sheet of paper appears white, all the colors of the spectrum are reflected off the paper. When the cover of your notebook appears black, none of the colors of the spectrum are reflected. They have all been absorbed. Light does more than illuminate our world, it colors it. Light waves are just part of the electromagnetic spectrum, the visible part of waves of energy that pass through our world. In the visible spectrum, the distance between the crests of the waves is greatest with red light. But there are light waves with a slightly greater distance between crests. We just cannot see them. Those are infrared light waves, sometimes called hot light. In the visible spectrum, the distance between the crests of the waves is smallest with violet light. But there are light waves with a slightly shorter distance between crests. We just cannot see them. Those are ultraviolet light waves, a form of radiation that gives us suntans. In addition to ultraviolet and infrared waves that we cannot see, there are other waves of energy beyond the visible spectrum, including microwaves, radio waves, X-rays, and gamma rays. There's certainly more to the form of energy we know as light than simply flicking a switch and illuminating a dark room. Light sustains our world. Wow, what an interesting book. I hope you learned something. I know I did. Keep up the great work, my friends, and I'll see you in the next video, okay? Bye-bye.